So what does a desk fan and an electric car have in common? They both use motors. What do motors do? So if we look inside, we see that motors cause things to spin or move. They use something called the motor effect, which has two key ingredient parts. First, you need a current going through a coil, and you need some kind of magnets inside, so a magnetic field inside it. So this uses something called the motor effect. So in a motor effect, there's some magnetic field there, and then you have a wire or a coil of a wire, and you pass a current through it. When the current goes through it, the interaction causes a force on the wire, and we can use this to make something spin or move. Let's look at it in a bit more detail. So here's a magnetic field from the permanent magnet, but it can also be from some kind of electromagnet. It can be any kind of magnetic field. And the wire, if we put a current through the wire, we learned a few lessons ago that this produces a magnetic field around it. And I'm going to take this wire, I'm going to put it inside the other magnetic field, and these two magnetic fields are going to interact. They're going to add and subtract. If they're in the same direction, they add. If they're in opposite direction, they subtract. When the fields interact, this produces a magnetic force on the wire, which is going to cause it to move. And if we design it correctly, we can make it spin like in a motor. Now, this doesn't always happen. If the current and the magnetic field that's already there is in the same direction, they're parallel, then there won't be any force. Or also if it's in the opposite direction, if they're anti-parallel, there's no force. So the magnetic force is zero if the current and field are in the same direction, or in other words, if they're parallel. However, if we put them 90 degrees to each other like this, so the current is flowing towards us and the field is going towards the right, that's when you get maximum force. If you have an angle in between, then you get some intermediate force. So to get maximum force, you need to have it perpendicular, in other words, 90 degrees. If it's parallel, if it's in the same direction, the field and the current, then you get zero force. Okay, example 1. Explain why closing the switch causes a movable rod between the magnets to move. Okay, so let's look at the image. So you've got these metal rails, and on the metal rails, there's a movable rod that's resting between them. And then you've got these magnets above and below producing a magnetic field through it. If we close the switch, well, we need to explain what's going to happen. So that's what the question is asking. Let's close the switch. We know current is going to flow. And when the current flows, it turns out the movable rod is actually going to move towards the right, there, like that. So why does that happen? First of all, when we close the switch, there's going to be a current flowing. So that's the first keyword. When the current flows through the movable rod, it's going to produce a magnetic field around the movable rod. But there's already a magnetic field there from the north and south poles there. So those two magnetic fields will interact with each other, and it's this interaction that produces a force on the movable rod pushing it. Part B. Another student sets up the equipment, but as shown in the diagram there. Explain why the rod doesn't move in this situation. Okay, so, well, if I close the switch here, the current is going to be flowing from positive to negative, so it's going to be going towards the left. But the magnetic field is going from north to south, that's towards the right. Well, that's basically parallel. So if the current and the field are parallel, then the fields actually can't interact with each other, and therefore there's no magnetic force on the rod.